Right, in this video we are looking at elasticity, but before we start I've got a little starter activity for you to do that looks back to what we did last lesson on terminal velocity. So what I want you to do is rearrange the bullet points in order to make a paragraph about terminal velocity. So pause the video, have a go, and then we will go through the answers. Right, so first thing, on leaving the plane, the only force acting is the weight acting downwards. Then second, that causes the parachute to accelerate. The parachute accelerates. As the parachute falls, the air resistance acts upwards. And then for number four, the weight is greater than the air resistance. As velocity increases, so does the air resistance, and terminal velocity is reached when the air resistance is equal to the weight. So, on to elasticity. When forces act on objects, they cause that object to change shape. An elastic object is one that returns to its original shape after it has been stretched or compressed. Now, quick thing to think about, why do we need more than one force if we're going to stretch, compress, or twist an object? Well, the reason for that is if you try to do that with just one force, you're just going to move the object rather than causing the change in shape. Okay, so 3 different types of materials you need to know about. The first is elastic materials. For an elastic material, the force is directly proportional to the extension. That means we get a nice straight line graph on a force extension graph. If deformation is elastic, remember, it returns to its previous shape when the forces are removed. If it's inelastic, it stays deformed when the object is removed. Now, rubber, for example, an elastic band, isn't elastic. It shows a force extension graph that looks something like this. It's not a straight line, so it's not an elastic material. But it does return to its original shape when the force is removed, so it shows elastic deformation. So it's really important to see that contrast there. The other type of material you need to know about is a brittle material, and brittle materials break without being extended very much. So you can see it doesn't go very far on the extension axis before it breaks. Okay, so what I'd like you to have a go at is I'd like you to plot a graph of this data and work out what type of material is being stretched. You don't need to use graph paper, use whatever paper you have available, and then we'll go through and see what type of material it is once you've had a go at that. So pause the video while you do that. Right, so you should have found that you got a straight line through the origin, which tells us that it is an elastic material because the force is directly proportional to the extension. Okay, remember, for directly proportional, we are looking for a straight line through the origin. As one thing doubles, the other thing also doubles. Right, moving on, we're going to look at something called Hooke's law. Now, Hooke's law is about the extension of springs. It says that the extension of a spring is directly proportional to the force applied to it up to the point called the elastic limit, and that's where it stops being a straight line. So the equation for that is force equals Ke, and that is one you need to learn, where F is the force in newtons, E is the extension in meters, and K is the spring constant in newtons per meter. It also applies to compression. We could use the E as the amount of compression instead of the amount of extension. It works just as well. Okay, so I'm going to show you an experiment. I'd like you to record the results using an appropriate table, and I'd like you to draw a graph of your results. Again, if you don't have graph paper, don't worry about it. Just use any paper you have. Force needs to be on the y-axis, extension needs to be on the x-axis, and you're going to plot points as a line graph, and then draw a line of best fit. Okay, so what we've got here is a spring attached to a clamp stand, and the first thing we need to do is measure the unextended length, and that is going to be 2.2 centimetres. Okay, so we've got our unextended length, then we're going to add our first mass to it. We're going to add 1 Newton. And then we measure it again, and that is 5.5. So to find out what the extension is, you need to do the original, the length we've just measured minus the original length. Okay, I'm going to make that up to 2 newtons. And then we're just going to wait for it to stop bouncing around. And that is 9.3. Okay, 3 newtons. And we are at 13.3. 4 newtons. Gives us 17.2. 5 newtons gives us 20.5. That's 6 newtons. 1, 2, 3, 4, 5, 6, yeah. Will give us 24.6. 7 newtons gives us 27.9. 8 newtons gives us 31.8. And then it falls over. Okay, so what I'd like you to do now is I'd like you to try and find the spring constant from your graph. The spring constant is the gradient of your force extension graph. So what you need to do when you've got your graph on the straight line bit, because it might curve off at the end, you need to pick 2 points that are on the line of best fit. They do not need to be points that you've plotted. And you need to find out the positions of those points. So if we have a look on here, we've labelled y2 and y1, x2 and x1. So our gradient, which is going to be equal to the spring constant, is equal to y2 minus y1 divided by x2 minus x1. And hopefully you've done gradients in maths, so that should be familiar to you. Okay, work done on a spring. When a force stretches or compresses a spring, it does work, and elastic potential energy is stored in the spring. If the spring is not inelastically deformed, the work done on the spring and the elastic potential energy are equal. You get given this equation on your data sheet. The elastic potential energy is equal to half times the spring constant times the extension squared. Okay, so you don't need to learn this one. Okay, so the last thing I want you to do today is I'd like you to work out the energy stored in the spring from the experiment in your graph. So we do that by working out the area underneath the force extension graph. So if our force extension graph looks like this, we block off the triangle at the end, and then we're going to use the equation for the area of a triangle, which is area equals half times base times height, to work out what the energy stored is, because that's the area under the graph. So half times base times height, and that should give you your answer. Remember, energy is measured in joules. Okay, so what I want you to submit for this lesson, I would like you to submit your table of results, the value that you calculated for your spring constant, and the value that you calculated for the energy stored in that spring. Okay, thank you very much.